All right, let's get straight into it. Welcome to This Explainer. Today, we're diving into a genuinely fascinating new theoretical physics paper by Mohammed Rabi Abdallah. And look, if you're tuned into this, you already know the stakes. We're talking about trying to bridge the most massive, stubborn gaps in our understanding of the universe. We're unpacking what's being called a quintuple unification. It introduces the BTR/DEC hypothesis and maybe most excitingly, a brand new particle called the Entropon.
Now think about this for a second. Imagine if a single mathematical framework could simultaneously eliminate black hole singularities and fully explain dark matter. Usually, theoretical physicists tackle these as completely isolated problems, right? Singularities are a gravity headache, while dark matter is a particle physics mystery. But here, we're looking at a unified framework that acts as a fundamental mathematical patch for the universe itself, aiming to solve both of these colossal mysteries in one swing. So here is our roadmap for today. We'll start with the fundamental crisis in modern physics, explore a proposed cosmic break for gravity, verify the math to ensure no theoretical ghosts pop up, meet a brand new particle called the Entropon, and finally, lay out the ultimate X-ray test to prove it all. Let's do it. Section 1. The crisis in modern physics, general relativity versus quantum mechanics. We all know the drill here. We have two wildly successful theories that essentially refuse to play nice together. It's the classic unstoppable force meeting an immovable object. On one side, general relativity. It beautifully governs the macroscopic cosmos, the heavy hitters, the high curvature stuff like stars and galaxies. But it has this fatal flaw, where it predicts its own breakdown, allowing for gravitational singularities where physics just gives up. Then on the other side, quantum mechanics governs the microscopic realm flawlessly, but it completely relies on a fixed, flat background of spacetime. You smash them together, and the math just explodes. To unify them, we really need a foundational principle where dynamics emerge naturally, without these universe-breaking contradictions. Section 2. A cosmic break for gravity. Introducing the BTR/DEC hypothesis. Okay, so to fix this massive incompatibility, Abdallah proposes a radical new framework. It's called the BTR/DEC hypothesis, which stands for entropy-regulated spacetime or dissipative entropy correction. Simply put, this theory suggests that the fundamental rules of spacetime have a built-in limit, and that limit is governed by entropy. It's constructed from the least action principle, which, as you know, is basically nature's way of being as mathematically efficient as possible. So instead of gravity pulling endlessly until space just tears into a singularity, this hypothesis introduces a unique nonlinear entropy-regulating correction. Space literally has strict mathematical boundaries based on entropy. And the absolute crucial piece of this puzzle is a value called R max. Think of it as a literal cosmic break for gravity when things get way too dense. R represents the Ricci scalar, our mathematical measure for how heavily curved spacetime is. Now, in standard general relativity, R can mathematically just shoot off to infinity inside a black hole. But in this new framework, nope. There's R max, a universal maximum curvature threshold. The universe simply is not allowed to bend past this specific point. So here's how this actually plays out in reality. Say a massive star collapses. Step 1, the spacetime curvature, R, approaches that absolute limit, R max. Then, step 2, this mathematical entropy-regulating term kicks in, and it actually grows to infinity faster than the matter density does. So by step 3, gravitational collapse just halts. Mathematically, it stops completely before an infinite zero-point geometric singularity can ever form. The universe, in a way, mathematically protects itself from breaking. Section 3. Banishing ghosts and tachyons, looking at the mathematical rigor. Because let's be real, anyone can invent a theoretical fix to stop a singularity. But does the complex math actually hold up under real scrutiny? Well, usually when you introduce new rules, you accidentally summon mathematical monsters, negative energy ghosts, or timeline-ruining tachyons. But through rigorous stress testing, specifically Jordan to Einstein frame transformations, this highly complex math maps cleanly back to standard functional forms. It satisfies vital stability checks, like the Starbinsky stability condition. Because the equations remain strictly second order, it completely eliminates those phantom Ostragadsky ghosts. And since the effective mass squared of the new field is positive, it avoids tachyons entirely. The math is, quite frankly, beautifully stable. And crucially, it completely preserves relativistic causality. The dispersion relations force the new field's group velocity to be strictly bounded by the speed of light. Plus, it mathematically guarantees that gravitational waves still propagate exactly at the speed of light, c. So no weird time travel, no breaking the universal speed limit. Everything stays perfectly causal.
Which brings us to Section 4, Meet the Entropon particle, the answer to dark matter.
We've got a stable, regulated spacetime, but what else does this math create? Well, when you take this entropy-regulating field and apply quantum mechanics to it, quantize it, the math naturally spits out a brand new microscopic particle. Abdallah named it the Entropon, represented by the Greek letter phi. It's a novel scalar boson. And the beautiful thing here is that this isn't just some random particle tacked onto the theory to make it work. It originates directly from that exact entropic gravitational coupling that prevents those singularities we just talked about. And because it emerges from such strict mathematical conditions, we don't even have to guess its properties. The paper calculates the exact mass of this theoretical entropon particle to be precisely 6.3 kilo-electron volts, or keV. Now, that is incredibly light, but as you'll see, it packs an absolute cosmic punch. Check this out. Assuming an initial field displacement of roughly 0.0063 Planck masses, the predicted relic density of the entropon perfectly matches the exact dark matter density observed in our actual universe today, right at that 0.12 mark. The very mechanism mathematically keeping black holes from collapsing into impossibilities might literally be the invisible web of dark matter holding our galaxies together. That is just incredible.
Section 5, the ultimate X-ray test, falsifiability, and future observation.
Because a good scientific explainer doesn't stop at elegant math, right? We absolutely need falsifiable, testable predictions. Well, the entropon runs the gauntlet and survives. It passes the stringent Big Bang nucleosynthesis constraints. Its effects on cosmic microwave background anisotropes, mathematically negligible. The 6.3 keV mass perfectly satisfies the Lyman alpha forest constraints, and it's totally consistent with historical X-ray halo observations from telescopes like XMM Newton. It is completely consistent with every major observational check we currently have. But the ultimate test relies on one highly specific number, 3.15 keV. According to the framework, the entropon should naturally decay into 2 photons over massive timescales. Since its mass is exactly 6.3 keV, the energy of each resulting photon is simply half of that. This creates a specific monochromatic X-ray spectral line exactly at 3.15 keV, a cosmic fingerprint just waiting to be found. And here is why this is so incredibly exciting right now. This specific 3.15 keV X-ray signal emanating straight out of the Milky Way's dark matter halo falls squarely within the sensitivity projections of the upcoming Athena X-ray observatory. We can literally point the advanced Athena observatory at our own galaxy's halo and hunt for this exact decay signal. If we see that photon flux, we have a direct, falsifiable observation proving this theory. So I'll leave you with this final, thrilling thought. If the Athena observatory actually detects this exact 3.15 keV signal, will we have finally unified general relativity and quantum mechanics? Just let that sink in. A single particle, born from the very math that stops black holes from breaking spacetime, could completely explain the dark matter building our galaxies. Are we literally just one satellite launch away from solving the greatest, most stubborn mysteries of our cosmos? It is an absolutely wild time for physics, and I hope this explainer helped you see exactly why.